So.
Okay, looks like we can start. Welcome back, everyone. And thanks for making it today. I found usually the last class before going into a holiday, whether it's spring break or Thanksgiving break, is usually the hardest one to attend. So good on you for making it in today. And even if you see the video later on, you were here in spirit, so that's good enough for me. But welcome back, folks. I don't have a lot of announcements other than our next week, we're going to be taking the entire week off for the Thanksgiving break. If you're still working on homework, if you're using that as a catch-up week, that's sometimes how it goes down for me on Monday and Tuesday at least. I will be available by email. I just have a habit of checking in on the morning. So if you're submitting homework, if you have questions that you want to talk about, don't hesitate to write. I'll be happy to help out. And pretty much why this is kind of a catch-up week for me on this Monday, Tuesday usually, of Thanksgiving break, is because I'm going to be mostly working down here, filling out the information for the final exam, the coverage, the review problems, and that kind of stuff. So if you want to take a look into final exam review questions a little bit earlier, it'll be available sometime over this holiday week here. So we're running out of weeks. We're on week 13. Next week is going to be, well, not next week, but the week after the holiday, week 14. We're going to be in December, and you'll notice the due dates for these sections are in December. Doesn't make sense to make things due on a holiday week. That's kind of seems cruel in a way. But for this week, we'll just have a normal Monday, Wednesday. We'll still cover content on Monday, but I'm going to try to make sure we end at a spot that makes sense. And then whether it's a full day on Monday, Wednesday is going to be just dedicated for talking about and reviewing for the final exam. So we're not going to be covering new content on Wednesday of this week. Then we don't meet at all on finals week. It's just going to be another final exam. I'll send exams over to either the Idaho Falls Testing Center, the Pocatello Testing Center, and the other testing centers as well. I'll still be available for questions and such during finals week. But that's pretty much our plan for the rest of the semester. We're nearly there, closing out week 13. So that's what we've got going on so far with the announcements. Any questions at the moment, folks, before we start today? Oh, great question, Chan. For the math department policy, final exams for all classes are to be set at 2 hours, which is quite a lot. It's kind of a shock for this class because we're used to 50-minute exams. Really glad you asked about that. Our final exam is a 2 hour final exam. Well, I'm not going to try to write an exam that goes 2 hours. You have to be writing the entire time. Typically, what I'm writing an exam for is right around the range of about an hour and a half. So the last 30 minutes that I'm going for are mostly meant for you to check your work, double check your thoughts, those kinds of things. So it's not going to be a very long, long exam, but the official exam time is going to be 2 hours. And another great question. Thanks for asking that, Alex. Will the final exam cover all material this semester or just the new material? It will be a comprehensive exam. So it's going to cover all the material in the semester, which means I can't actually ask every single question from every single section. So I'm going to be kind of cherry picking kind of the main ideas on a chapter by chapter basis. There's not going to be any emphasis on one section or another. So for example, exam 3 ended on section 7.2. It doesn't mean I'm going to ask a whole bunch of 7.3, 7.5, 8.1, 8.2, and 3, and so on questions. It's going to be kind of an even weight on each one of the chapters. And those are really good questions about that. That's one of the reasons I like to show what are some great review problems for the final exam. I even present old final exams, real final exams in prior semesters, so that you get a real feel for what does a 2 hour exam actually look like, what kind of questions are being asked. So you'll have a little bit more to prepare for the final exam than you did for exams 1, 2, and 3 in that certain sense, which I think is fair because kind of how Chan was asking, going from a 50-minute to a 2-hour exam is a pretty big change. Well, other questions at the moment? Okay, these are great questions about the final exam in particular. We're really getting close to that point. One thing I do want to mention though, when it comes to the final exam, my goal is not to write an exam that's going to be like soul crushing. Like I mentioned, I'm not going to try to write an exam that you have to be writing and thinking as fast as possible for 2 hours. That's kind of inhuman in a certain sense. I don't think a lot of people can be on for 2 hours straight and come out normal after that experience. And usually when I write a final exam, kind of my goal is to not really even change the course grade on average. In fact, when I write and grade the final exam, I take a look at the actual average course grade before the final exam and after the final exam. And if I notice, say, the average course grade got dropped by around 3%, 5%, something like that, that's the one exam that I do curve in the semester. So I'm trying to bring everyone back to a baseline of 0 after I curve that final exam, not trying to write the world's most despisable kind of exam in a math class. So think of the final exam as just a formality. It's something we have to study for, be prepared for, but it's not meant to knock your grade down or anything like that. But I think that's my last thoughts about the final exam. We'll talk about it a little bit more as we get closer and closer to finals week. So far we're in section 8.2. We'll start section 8.3 today, more likely than not, but we'll be revisiting it when we're back on Monday after the break. Any last questions at all, folks, before we go back to 8.2? Okay, well, let's jump back to that section. Section 8.2, it was all about the law of cosines. The law of cosines has the relationship between angles, alpha, beta, gamma, or if you call them, say, capital A, capital B, capital C, same kind of relationship. We have the capital A, B, and C in this triangle down below. And it's a relationship between an angle, say gamma, and the opposite side length, say C. Looking at this one, this would tell us C squared is equal to cosine gamma on the very far right. But notice the A and B's show up in these two, well, really 3 different terms. These are the 2 angles that give the interior angle gamma. So really that's the whole entire relationship for law of cosines. Whether you're trying to solve for side length A, B, or C, these would be the 3 good equations. But you know, it's not always about solving for the side lengths like A, B, and C, as we see here solved for. Sometimes the reason you need law of cosines is because you're trying to solve for an angle in the very first place. And that's what example 2 is all about. We know all the side lengths of this particular triangle, but we don't know a single interior angle. We just know triangle is built out of these 3 different side lengths. But that's okay. Law of cosines will allow us to solve one of those angles if we so choose. Let's go for cosine uppercase A, just because the red dot was parked there. That means if we start off this problem, let's say we're using law of cosines just to say what law we're using. Then the side length that we're focusing on is this A here, we'll square it, and the angle we'll be solving for would be cosine of that angle A. So let's write out the law. We have A squared is equal to B squared, so that's this side length, and then this side length, squared, B squared plus C squared minus 2, so that's where the -2 factor comes from in the formula. Take whatever side lengths you built out and just repeat them again, -2 times B times C times cosine of that angle A. So that's our law of cosine started. Now we're just going to plug in the information we have. A squared on the left is going to be 15 squared equals, we have a 25 and 28 for B and C. So 25 squared plus 28 squared minus 2 times, say numbers again, 25 times 28. And the angle A is unknown, so just cosine A again. I'll leave it just this way, no longer color coded. We didn't make a substitution there. But now we just throw all this into the calculator. 15 squared, you usually remember that one, but it's probably too late for me to remember that today. So grab your trusty calculator. 15 squared is a 225. 25 squared plus, let's just add both these terms together in the calculator. 28 squared sums to 1409. So 1409 for those first two terms. Then minus, let's just crank out 2 by 25 by 28. We get 1400 exactly on that. Cosine A. So now we've got a nice equation where we just have to take two algebraic steps. Subtract 1409, divide by negative 1400, and you've solved for cosine A on this equation. Any questions at all, folks? Running through the calculator to this step? Okay, let's do it in stages, just so the notes don't look as mysterious. Take 225, subtract 1409, and we get negative 1184 equals negative 1400 cosine A. Then divide the negative 1184 by negative 1400. Should have put parentheses around there. So divide that by negative 1400, and we get in the calculator, even if we're rounding to the nearest tenth, this is an intermediate step, a step in the middle. And this is an angle that we're going to be trying to solve for next. So I'd say 4 decimal places is a good rounding part for this kind of work. Whenever you have cosine A equal to something, and you're about to use cosine inverse. So let's go 0.8457 on this one. Equals cosine A. But this just takes us back to, excuse me, section 7.5, solving a trigonometric equation. We know the goal here is to just take cosine inverse of both sides, the last two problems on those notes, and same on the homework exercises. But we also know that we might have to be a little careful that we get the angles we're expecting. For using cosine inverse, we're going to get something in the domain of 0 to pi. And let's put this in degrees, which seems to be the theme in chapter 8. Pi is 180 degrees. The value for cosine is 0.8457, which is somewhere about here. So when we go to use cosine inverse, we're getting a measurement right over here. So this little dot on the x-axis is just the 0.8457. And yeah, cosine inverse is giving us the right angle between 0 and pi. If I had something a little bit different, say maybe a negative value, I probably would get the right value as well, here to here. The angle A we know is between 0 and 90 degrees, so this fits the picture that we're about to produce using cosine inverse. So next step, take cosine inverse of both sides of the equation. Cosine inverse 0.8457. Cosine inverse of cosine A just gives back the interior angle A right away. And so now it's just another calculator operation. Double check in your calculators before you punch this in that you're in, let's see. I want to put it in degree mode. If you gave me an answer in radian measurement, that'd be just fine, but it seems like most of the problems in the notes here are in degree mode. So let's keep this in degrees as well. So let's do cosine. That's the wrong function. Arc cosine is how I call it in this calculator. 0.8457. And that's the angle measurement we would get. Let's round this one to the nearest tenth. 32.2 degrees. And to the eye, that does look about right, as well as right over here on this quick sketch we put down. So 32.2 degrees is A. And that means we are 1/3 of the way down. We've got the interior angle A here measured, 32.2 degrees. If we can get the other two angles, our work is done. Well, that's another take at the law of cosines. But one thing you might have noticed is law of cosines is a good amount of work to do. It's a lot of number crunching. It's not the worst work in the world. But if you make a simple mistake, I recall making another mistake on this one, just writing down the equation, then it can be a frustrating law of cosines to use. So you could use law of cosines to find angle C, law of cosines again to find the angle B, but that's not necessarily working the smartest. What I would do at this stage is, you might have noticed the law of sines goes a little bit faster for just about every problem of this type when it works. So let's change gears, solve for angle B, but let's do it with the law of sines approach. Really, section 8.1, 8.2, they don't exist in isolation. They really go together. So this is a great spot to review how law of sines would go. Law of sines, next. We're going to deal with this angle B and the opposite side length of 25 meters. And write out, let me get my colors going first. We'll write out that sine of angle B divided by the side length of B is going to be equal to, we can't use C to C here because the angle C is unknown, but we solved for the angle A, so we'll use sine A divide by the opposite side length, lowercase a. So using law of sines like that, we can solve for the angle B probably a good amount faster than what we did over here to the right on law of cosines. B is the unknown, so we'll just write in sine B. Divide by lowercase b, 25 meters. I'll just write it in as a 25. The unit's going to cancel in the next steps. For sine A, we have 32.2 degrees. So sine 32.2 degrees divide by the side length A, which is 15 meters. Next, clear denominators, multiply both sides by 25, and we have sine of B is now equal to 25 times sine 32.2 degrees divided by 15. And it's back to the calculator at this stage. A lot less calculator work though. Just a quick fraction to compute. We have 25 by sine 32.2. This calculator is already in degree mode. Divide by 15. And it comes out as 0.8881. So sine B is 0.8881. Again, 4 decimal places is a good call. It's kind of like working with exponential functions. If you round too bluntly at first, your end answer could be pretty wildly inaccurate out of nowhere with it. Functions like exponentials and trig functions. So sine B coming out as a 0.8881 means over here, we'd be about on this end of the diagram. We're going to use sine inverse, and sine inverse goes from negative pi over 2, which is negative 90 degrees, up to positive pi over 2, positive 90 degrees. And it's only going to give us an angle from those two spots. But that would give us the right angle. We're expecting an angle somewhere around here. This looks like it's maybe around 45-ish degrees. That looks like it would fit for this picture right here. So using sine inverse, you're only going from here to here, getting one answer, and that looks like it'd be the answer that fits. So back down here, same approach with the law of cosines. Take sine inverse of both sides. B is now sine inverse of 0.8881. And this will give us the angle B. So back to the calculator once again. Heavy calculator work for this section. But it's an applied section, so it's expected. Arc sine, 0.8881, is giving us 62.65 degrees. I was estimating like 50, I might have said, 45, I might have said, but 60 actually fits a little bit better on this picture now that I'm looking at it. Rounds to about 62.6 degrees. Let me box out where our answers are ending up, just because we have math just sort of exploding all over the place with the different approaches. But 62.6 degrees gives us this angle now. So law of cosines cracked open the problem. It got us one angle. With one angle, you have a foothold. You can use law of sines. And now we are delving further into the problem and got the next angle, 62.6 degrees. And then over here, you could use either law of cosines or the law of sines, or just use the fact that the sum of the interior angles of a triangle must add up to 180 degrees. That'd be working probably the smartest way. You're taking the least amount of steps, making you the most accurate possible. So the last approach is the sum of interior angles equals 180 degrees. And that as a concept allows us to solve for angle C. C is now going to be equal to 180 degrees, subtract angle A, the first angle we found, 32.2 degrees, subtract again angle B, 62.6 degrees. And our job is done right at that step. I think I still need a calculator for this. Notice that looks like it's close to 90 degrees, at least by my eye. We're going to see what it is really now once we go to compute this. 180 minus 32.2 minus 62.6 comes out as 85.2 degrees. It was just shy from being a right triangle by that amount, less than 5 degrees. So 85.2. And there we have it, folks. We could not have started this problem in a normal, easy way without the law of cosines. We might have had to get some specialized tools like a compass and protractor kind of set up. But solving it mathematically, really all you need is a law of cosines. You don't have to make any specific by hand measurements. In fact, that's dangerous to do because there's no guarantee that everything is proportional here when we see these kind of figures produced. All we know for sure is the measurements, and we didn't want to rebuild it from scratch just to find those angles. So we've got it, folks. Any questions on basically the tour of what we did last Monday? Okay, we'll do one more application problem and then take a look into the next section, polar coordinates. So here's that last application problem. It's another surveying kind of application. We're told a surveyor has taken the measurements shown in the diagram below. So it seems to be some kind of maybe something you might see in Idaho, some kind of random lake we're looking at. Find the distance across the lake. That's pretty blunt instructions. That's all we're doing, finding the distance of this dashed line to the nearest 10. That's a pretty interesting problem. Maybe not as practical as the last application problem we solved. Let's think about the last application before we go to solve this one. This is still a pretty cool problem, the fact that we can find this distance with these three pieces of information. But looking at what we did in section 8.1 of law of sines, I think that's almost a kind of a miraculous problem that mathematics works out the way it does in this one. In this last problem down here, all we knew is the distance between two stations that can make accurate angles, and there's great tools for doing this, for something that's way out there. We had two accurate angle measurements, a distance between the two stations, and we could find the distance from any object out there that we've identified the angles to this line right here, right where that line intersects between, or goes from A to B. So that was a pretty amazing kind of problem. This one is also pretty neat, but notice the trouble with it. You still have to make that angle measurement. That's the same as the last problem, but you have to measure this specifically. So that's a lot of work, getting those specific measurements out. I mean, there's ways to do that, right? But if you just knew this one measurement and this boat moves to any random direction whatsoever, you'll always know this vertical distance back to the shoreline, which is a pretty amazing kind of process on example 5. But not to knock this one too much, it's still an interesting problem, and we can solve it directly with law of cosines. This is basically law of cosines best case scenario setup. The minimal information you would need to get, the one thing you're solving for, it's going to be the distance across the lake. So that value D right here. If we had used law of cosines on this, you would have to have the angle on the other end, which we do, you'd have to know the lengths of both sides for which that angle is interior to. We know that as well. And so that means we're completely set up right here for law of cosines. We can just use it immediately. Law of cosine says that the distance squared, and you could say distance equals square root and everything on the right-hand side if you really wanted to. That's totally up to you. I usually like using it in this format, the law of cosines, just direct statement. So I'll take a square root as an additional step as I go through. Let me make sure I have enough horizontal space as I write this out. Distance squared is going to be equal to, take these two side lengths, square them, so 800 feet. I'll drop units here and just write in 800 plus 900 squared. Next part of law of cosines is you go minus 2 times those same measurements, 800 and 900. Then multiply that by cosine of that interior angle measurement, 70 degrees. So as long as this distance you want to find is opposite of the angle, we're all set up if you can plug in those two pieces of information. And that makes this kind of the quickest problem in the entire set of notes, because everything on the right-hand side, you can just put into the calculator as one line if you chose to. Any questions at all, folks, with just the setup itself? Okay, let's put it into the calculator. So right-hand side is, let me know if I mistype anything, 800 squared plus 900 squared minus 2 times 800 times 900 times cosine of 70 degrees. I get a pretty large figure, but remember that's the distance squared, so we have an extra step. 957, 490.99 is what I'll write. Let me double check. And let me see how good my memory is doing today. It's a lot of digits for me today. Way off, 957, 490.99. I should probably double check that again, so let's see how we're doing. 957, 490.99. Okay, randomizing digits that feel random is not quite my strong suit, but we'll always get through it. So now take square roots. The distance is the square root of that number above, 957, 490.99. We're rounding to the nearest tenth, so that should be enough accuracy to get us accurate to the nearest tenth upon rounding. So one more quick stop at the calculator. I'll go square root. And just to be more accurate, let's just copy that in. Throw that figure in, and to the nearest tenth, that's 978.5 feet. That looks commensurate between the values that we saw in this diagram. Again, we can't fully trust that this diagram is perfectly proportional to scale. We would have to have an additional statement that would say that, assume all angles, all side lengths are 100% proportional. But at least it seems comforting that the diagram isn't too off, too wonky. That feels like the right amount. So that's a pretty cool technique. If you happen to know these specific side lengths and interior angle, you can get a distance across. Who knows how they measured this? Maybe someone is doing something very specific, walking along a particular trail. I'm not exactly sure what the techniques are to get those best distances. But this one has, again, it's a well-defined problem where there's tools to get those angles. You find that distance exactly once, and you can always get the distance away from a vertical coming down on any object, wherever it is, however it moves. Both of them are pretty interesting problems in their own right, and this is where law of cosines shines the most. Well, any last questions at all, folks, about either section 8.1 or 8.2? Yeah, go ahead.
I bet they probably had someone swim down to the bottom of the lake with that measurement.
Swim down to the bottom of this lake to
Yeah.
get those two here to here?
That's what's in my head.
Gotcha, yeah.
That's what I'm thinking.
Yeah, it's kind of a random thought that you would know those two measurements specifically, which is hard to get exact values. 900 feet is a ways to go. And somehow you didn't have the tools to do this. You don't have a boat, but you can do that distance just fine. So yeah, I feel with you understand your comment there.
People for that.
Probably, yeah. Well, other questions or comments so far? Okay, well, these are pretty fun applications in trigonometry, and this is really what we're doing for the rest of the semester. The next section, 8.3 polar coordinates, is another kind of application. It's more of a mathematical application more than anything. And the last section we'll be looking into is applications to vectors, which is very well applied, whether any kind of sciences you might think of. Vectors are probably something that can come into play. We'll talk more about them later after the break. But as far as polar coordinates goes, I mentioned it's more of a mathematical application because you're more likely to see polar coordinates if you take, say, calculus 2 is where it comes up in one spot out of nowhere. The last part of calculus 2, say around this week, people start talking about parametric curves and polar coordinates comes up. And calculus 3 comes up in an even bigger way. Polar coordinates is a technique for finding certain kinds of volumes. So you start to expand into a polar coordinate system using these ideas. But the big takeaway is random ideas from trigonometry, if you know you're taking a lot more math classes, it shows up everywhere. It feels like no matter what math class you're taking, differential equations, linear algebra, calculus, engineering classes, chemistry classes, trigonometry is just going to show up. And this is one of those concepts that does show up a lot. We're teaching it here so that when you more likely to not brush up against it again and review it again in another setting, probably calculus, you'll have a good idea of how this all goes. So it's a cool process. We're used to, when we think of coordinates, thinking of the rectangular coordinate system, Cartesian coordinates. But there's a lot of different ways to write out a coordinate system. And now that we have a lot of trigonometry under our belt, this is just a new way to do it. In a certain sense, this might feel a little bit like how we started out class on week 1, day 1, when we were defining angles. There's a lot of overlap and carryover between those concepts. So here's how we're going to start. We'll begin by drawing a half line or ray. When we defined angles, we needed 2 rays, an initial ray and a terminal ray. But here, we just need one, and we're going to call it the polar axis. So here it is. Here's our half line or ray called the polar axis. It can go in any direction, but usually for the sake of our own sanity, we depict it as a horizontal line. It kind of just looks like the positive end of the x-axis, basically. So this is the polar axis. In the XY coordinate system, we have the origin, 0, 0 coordinates. Here, we have what's called the polar origin. Pole or origin, rather. I guess you could say polar origin, and that would be okay. So here's the origin, right at that spot. I'll say it as origin, or you could call it a pole if you prefer. And here's the part where we just drew it as essentially the positive end of the x-axis. So we're trying to define a coordinate system. If this is a coordinate system worth anything, you should be able to put a random point P anywhere. Let's throw it way over here. Here's our random point P, and we have to say, how do you get there? We just need 2 pieces of information to give coordinates right on P. We need R, the distance from O. Recall O is the pole or the origin. So here's uppercase O. Try to draw it sideways so it doesn't look like the number 0. I have a hard time with it because if I make it cursive, that looks like theta now. So that's kind of tricky in this class. So here's the origin O. Kind of doesn't look like it the way I draw 0. R is the distance from here to here. So let's measure that distance. From here to here, this is the distance R. Next piece of information we need is theta. it's gonna be the angle measured from the polar axis, this one we put here, and the line that goes through O, the origin, and P. So we need a new line. Let's go like that. Let me try again, last try. A little bit better. Here's the line. We measure an angle theta, so it goes off like this. This is an angle still measured in a standard position sense, in the sense that we would think of this as a positive angle because we're rotating in a counterclockwise direction. And then once we're here, we have the coordinates r and theta are the coordinates of the point P. So right here, this is r theta. So that's pretty much the whole system. This is the polar coordinate system. You can imagine as P moves anywhere, the angle changes. If I make it closer to the origin, the directed distance, lowercase r, would also change. It's just the distance from here to here. Let me see if I can write that r just a little bit more cleanly for the diagram. Distance from here to here is r. And that's the origin there. And so this is the entire polar coordinate system. That O is starting to look like a distraction. Let me take it off for the diagram's sake. There's a lot to talk about this because we know there's certain issues when it comes to trigonometry. If you took that theta and added 2 pi to that angle theta, what would happen? This arrow just rotates an entire revolution and ends right here. This tells us for this particular coordinate system, we do not have unique representation at all. And we lose unique representation in a lot of different, pretty surprising kind of ways. But that's what we're going to discuss next when we think about the coordinate polar system and go into the next examples. But this is the landscape so far. This is what polar coordinates looks like at the moment. Does it make sense on how we measure those coordinates for the point? Okay, just to add that last thought, that point in blue can also be described, not appropriate really to say equals, I'll just use a comma to say another description of that coordinate is r, comma, theta plus 2 pi times k. That might feel familiar, where k is any integer. So we, in a really huge way, have lost unique representation. Every single point in the polar coordinate system can be represented in infinitely many different ways. Makes it seem like kind of a strange coordinate system, but it absolutely has its uses. At the very end of the notes, we'll see some hints on why it's a useful coordinate system when we look into equations. So if k is 1, that's 1 full revolution going in the clockwise direction. K is, say, -6. That's excuse me, 3 full rotations in this direction, the clockwise direction. So about like that. K can be any integer whatsoever, and we have the same description. The origin itself is kind of interesting because if you try to measure it with a directed distance, r, that distance should be 0. So right on the origin, the pole of the polar axis, this can be described as 0 theta. And you can pick whatever theta you'd like. Any value of theta would work here because it doesn't matter if you rotate, if you never went any distance out, you're still just at that point where the red dot is. So this one also has infinitely many ways to represent the origin now. Any angle theta whatsoever does the job. And it gets even weirder. This point, r theta, much like that point that we plotted down, could be represented as -r theta plus pi. It's in that sense that we call r a directed distance. R is the distance from the origin to a point, but r could be 0 if we're here, and it can even be negative, which kind of seems strange whenever we say distance, but the directed allows for negative as well. We'll draw an example of what that would look like right down below, just to get a feel for what's going on with this very last sentence. So to do that, let's plot this particular point. plot r theta equals, let's let it be 3 and go for, how about something familiar, like say a pi over 6. So we've got a distance 3, we've got an angle pi over 6 we're going to work with. And the moment it says r theta equals, it's telling us the plot is really going to be in the polar coordinate system. So much like the diagram above. So if we go to make that plot, here's what it's going to look like. Here's the polar axis extending to the right. We have to make an angle measurement at pi over 6. The pi over 6 is just 30 degrees off of this polar axis. So it would be going off in this direction. To my eye, that looks like about 30 degrees. So I'll put here on the end, much like what we did in the prior chapters, pi over 6 is just saying this is the measurement on the terminal end of this ray coming out. We have to go 3 units along this length right here. So here's 1, 2, 3. And we just make the measurement, or put down the coordinates rather. We've already made the measurement. 3 and pi over 6. So here's 3, here's pi over 6. But we're told by this sentence that r theta we just plotted down can also be represented as negative r theta plus pi. So let's look into that new concept next. Also plot negative 3 pi over 6 plus pi. First, let's just do some quick arithmetic on this. Pi over 6 plus pi is just pi over 6 plus 6 pi over 6, giving us 7 pi over 6. But 7 pi over 6 is related to pi over 6 in that you're just going in the diametrically opposed direction. Let me try a better line. You're going off in this direction now. So here's 7 pi over 6. And yeah, if you rotate for where pi over 6 was by 180 degrees, you end up at 7 pi over 6. So that's what's going on with the theta plus pi in this sentence right here. But now we have to decide, what does negative 3 actually mean in this particular situation? Well, what it means is you go to wherever pi over 6 plus pi is. Let's write this down as equals negative 3, 7 pi over 6, just for clarity. Okay, now ready to plot. You go to wherever 7 pi over 6 was. Here it is. Go back to the pole, and we want to go a distance on 7 pi over 6, negative 3. It means you're not going in this direction, you're going the opposite way. You're going 1, 2, 3 tick marks out that way in the diametrically opposed direction. So that's what the negative is really trying to say graphically, geometrically in the polar coordinate system. Negative just means go on the angle and move the opposite way. Go back to the pole, 1, 2, 3 to end here. So this is also coordinates negative 3, 7 pi over 6. Definitely weird, but it's something we get used to and practice with the more and more we take a look into this. Just for another quick concept, if we're plotting, say, negative 3 pi over 6, we would go to pi over 6, go the opposite direction, down 1, 2, 3, and this would be at negative 3 pi over 6 for the same concept. So the negative r value is definitely weird, and again, that's why it's called a directed distance. It can take on any sign, it can even be 0. Well, we've done it, folks. This is our crash course on the polar coordinate system. Any questions or comments about it so far? Okay, well, the best way to really get good at the polar coordinate system is practice plotting more points. That's what we're going to be doing in the notes. But you have to even go a little bit beyond that. You have to relate these points in polar coordinates to something that's familiar. In other words, if we can convert a point in polar coordinates, like 5, 7 pi over 4, back into the Cartesian coordinate system, rectangular coordinates, we get a good feel for how the new coordinate system is working. So that's what we would be doing in the next examples. We're going to convert between one coordinate system into the next. And these are the equations that do the job for us. This is relations between polar and rectangular coordinates, or Cartesian coordinates if you prefer to call it. You have x is r cosine theta, y is r sine theta. The purpose of these two equations are for converting from polar to rectangular. So they're nice equations. In fact, we could use them directly. The r value is 5, theta value is 7 pi over 4. So just crank these two equations out and we get the Cartesian coordinates. It's kind of a nice process. So this is the fast direction. It's fast to go from polar back into the xy Cartesian coordinates. And this is the not so fast equation. This is where it gets a little bit tricky. So this is going to be example 2. The purpose of these two equations are for converting from rectangular to polar form, or polar coordinates if you prefer to say. I ran out of space here. I'll call it form. What makes it tricky is not the first equation. We can take a square root and either take the positive r value or the negative r value. We saw in the last ideas that both values work. What's tricky is here. In a lot of cases, you have to solve that trigonometric equation, which means you're possibly going to be using a calculator like we did in our section 7.5 last couple problems. We have to be very mindful of domain and range to make sure we even get the right angle in the very first place. And so it's this part right here that makes this conversion a little bit more tricky. An inverse equation comes into play. My thought was before we did example 1, even though it's fast, I feel like justifying this a little bit is pretty helpful. If we had the time, we're kind of shy on time at the moment. What I want to do is drop in the polar axis, overlay it with the xy axis, the Cartesian coordinate system, and show where these equations really come from. It's in fact just a whole bunch of SOHCAHTOA coming out again, and Pythagorean's theorem is this one right here. But I think this is going to be something that'd be nice for us to come back to after Thanksgiving break. We'll refresh what polar coordinates are all about, look into this relationship a little bit closer. Then our goal is to do a plot and a conversion, another plot and another conversion. I think that's meant to be on the next page. Something with a distance formula where we plot a couple more polar points. And then this is the major reason why so far we can see polar coordinates are useful. We can transform these kinds of equations into polar form where they simplify. And we'll go backwards, taking something already in polar form and writing it into Cartesian coordinates, really just looking at these one more time. But again, I don't want to try to rush this and just cram it all in, right, before we're going on a big long holiday. We'll come back to this, refresh ourselves after we've had a bit of a break, and start from here, example 1. Well, any last questions at all, folks, with what polar coordinates are all about so far? Okay, well, have a great Thanksgiving break, folks. Try not to work too hard, but if you're turning in homework or if you have questions, I'm checking my email at the start of the day pretty much every day. It's just a habit at this point. But take care, and I'll see you all when it's, December 1st already is when we'll be back. Take care. Thanks, you too.